This is the fifth video in a series devoted to differential equations. And today we're going to look at so-called exact differential equations. But before we get there, we need to do a little bit of motivation. And so these are still first order differential equations. And let's notice or observe that any first order differential equation can be written in the following form. P of xy plus q of xy times y prime equals 0. And that's just from moving things around as appropriate. And so p and q are some functions that are functions of two variables. Or we could rewrite that derivative in Leibniz notation instead of Newton notation. And we'll have p of xy plus q of xy dy dx equals 0. So that's just rewriting this first equation. Or we could write this in so-called differential form or as a differential one form, which is getting a little bit outside the bounds of this course a little bit, but I think it provides a lot of motivation for this notation. And that essentially looks like we multiplied this entire equation by dx and canceled the denominator, although that's not exactly what happened. And now we have p of xy dx plus q of xy dy equals 0. So this is the way that these kind of problems are commonly written in this sort of differential equations course. But I find that a little bit strange because generally the background is not really there to use this notation. So you can really just look at this notation as a different version of one of these if you'd like. Okay, so let's maybe recall something real quick, and that is the differential of a two-variable function. So let's say that we're given some function f, which is a function of x and y, then its differential, or really this is also something known as its exterior derivative, is given by the partial of f with respect to x dx plus the partial of f with respect to y dy. And so what this is saying is that the output of the function is changing in terms of the partial with respect to x times an incremental change in the x direction plus the partial with respect to y times an incremental change in the y direction. I'd also like to recall that we have some simplified notation for these partials with respect to x and y, and that would be f sub x, and then we have dx plus f sub y dy. Now you can also think about this as running maybe in parallel or similar to the gradient of a function. So if we take the gradient operator of this function f of xy, that's going to be a vector field, and that vector field has components f sub x, f sub y. That's just kind of our definition. So you can think about this thing, which I earlier called a differential one form, as being related to this gradient vector field in some sort of way or another. And so how does this relate to our given differential equation over here? Well, it relates using kind of the following observation or thing that we'll note, and that is if the partial of f with respect to x is p and the partial of f with respect to y is equal to q, then the equation f of xy equals c is an implicit description of a solution y of x to our differential equation p dx plus q dy equals 0. And that's because if we take the differential of the left-hand side of f, we get f sub x dx, but that's just this p dx, f sub y dy, but that's just this q dy. And if we take the differential of a constant, we just get 0. So we've achieved this differential equation. Okay, and that really brings up the following pretty big question, which of course, like, our main goal is to solve differential equations. And so far we've just talked about how to re-envision a differential equation in terms of a function of two variables or something. So our big question is, when can we find a function f of xy such that f sub x equals p and f sub y equals q? So in other words, it's like a simultaneous x antiderivative of p and a y antiderivative of q. But let's notice that that's equivalent to the question, can we find a two variable function f of xy such that the gradient of f is equal to this vector field PQ? Well, if you've taken a multivariable calculus class, then you might know the answer to this question, and I'll just fit the answer to this question into this little box because the answer is quite short. And that is, if and only if the partial of q with respect to x, so in other words, q sub x equals the partial of p with respect to y. And that's equivalent to something called the curl of our vector field PQ being equal to 0. Okay, so we've brought up a lot of details from another course, a multivariable calculus course, which sometimes isn't even a prerequisite for a differential equations class. So let's review what we've seen so far. Well, we can take any first order differential equation and write it in the following form. And then we have a solution to that differential equation described implicitly by f of xy equals a constant, where this is a new two variable function f, if and only if, when we take the partial with respect to x of f, we get p, and when we take the partial with respect to f of y, we get q. But then the existence of this function is only guaranteed, well, maybe it's exactly guaranteed, when we have the partial of q with respect to x is equal to the partial of p with respect to y. And when this occurs, we'll label this type of differential equation an exact differential equation. Okay, so now that we've done all of that buildup, let's maybe get that kind of definition of an exact differential equation on the board, and then we'll start to solve some of them. So based off the development that we saw on the last board, we have the following definition. So we say a differential equation is exact if it's of the form p of xy plus q of xy times y prime equals 0, where the partial of q with respect to x is equal to the partial of p with respect to y. And like I said, we motivated this definition before. And furthermore, if we have an exact differential equation, then a solution to that equation, y of x, is implicitly described by f of xy equals a constant, where the partial of f with respect to x is p, this function up here, and the partial of f with respect to y is q, this function up here. And like we said before, this function capital F is guaranteed to exist based off of this exactness condition and some results from a multivariable calculus type class. So now let's go through some examples. And as you've seen in previous videos, once we've gone through a couple of examples, it's pretty easy to extend those as they all follow like a similar strategy. Okay, so our first example is 2xy minus 9x squared plus the quantity 2y plus x squared plus 1y prime equals 0. So I guess maybe the first thing we should probably do is check to make sure this thing is exact. So what does that mean? That means we need to take the partial of this guy with respect to x. So let's do that. So the partial with respect to x of 2y plus x squared plus 1, well, that's equal to 2x. Let's recall the partial with respect to x looks at all of the variables and it sees x as a variable, but it sees all of the other variables just as a constant. That's why the derivative of 2y is equal to 0 here. This is not like a total derivative where we know that y is a function of x. This is a partial derivative. Okay, now let's compare that to the partial with respect to x, or sorry, the partial with respect to y of this thing over here. So we have 2xy minus 9x squared. So let's notice that that is also equal to 2x. And that's because when we do this 2xy here, the constant in front of y is 2x. So that derivative is 2x. And then 9x squared is a constant. So its derivative is 0. But let's notice that everything checks out here. These two are definitely equal. 2x is equal to 2x. So this is exact. Okay. So now that we know that this is exact, let's state our goal just for good measure. Our goal is to find a function which we'll call f of xy such that the partial with respect to x is this guy right here. So 2xy minus 9x squared. And the partial with respect to y is this guy right here. So that's 2y plus x squared plus 1. Okay, and so there's two main strategies here. You can start with this kind of partial or this partial, take the antiderivative here with respect to x, or take the antiderivative here with respect to y. It doesn't really matter. I generally just start with whichever one looks easier. But that being said, here we've just got two polynomials, so they're all about the same difficulty. Okay, so for the purposes of this one, let's start with the one that I'll put a pink dot next to. Okay, so we've got the partial with respect to x of f is 2xy minus 9x squared. And now let's take the antiderivative of that with respect to x. So I'll write that as antiderivative with respect to x. Okay, so that's going to give me f of xy, but I'll leave off the of xy just so it's not as messy. And then here we'll have x squared y for this term. Remember, y is a constant. For this next term, we'll have minus 3x cubed by the power rule. But then, since we're taking the antiderivative with respect to x, we'll get a constant. But what do we know? We know that everything having to do with y is a constant. So what we really get is an entire function of just one variable y. So I'll call that g of y. Now let's just check to make sure this works. If we take the partial derivative of this whole thing with respect to x, we re-achieve this over here. So we're good to go. Okay, so now what we'll do from here is take the partial with respect to y and then look at it compared to this partial with respect to y. All right, so let's maybe have that be this yellow arrow diagonaling up. So I'll write this is the partial with respect to y that we're taking. Okay, so that's going to give us f sub y equals, so let's see, the partial of this with respect to y is x squared. The partial of this with respect to y is 0 because we only have x's. The partial of this function g with respect to y is g prime of y. So we've got x squared plus g prime of y. But then, because we've got this other version of the partial with respect to y that's like given from our setup, we've set up an equation. So this is equal to 2y plus x squared plus 1. But some things cancel. Notice that this x squared cancels with this x squared, and we've built a differential equation for y. And it's a fairly simple differential equation for y, and indeed, all of the time we'll build some sort of differential equation for whichever function we've built here, and these will always be pretty simple to solve. So let's see, if we know the derivative with respect to y is 2y plus 1, then that means that g of y is equal to y squared plus y And then I could say plus a constant, but I don't really need to do that because our constant is going to be wrapped up into this implicitly defined, or this implicit defining relation over here. Okay, so anyway, we've got g of y equals that, but now we can merge these two things together. So this g of y together with this capital F, so that tells me that capital F of xy is equal to, let's see, we've got x squared y minus 3x squared plus y squared plus y, and that's going to be equal to a constant. And that equation set up equal to a constant is our implicitly defined solution. And you might say, well, we could maybe solve that explicitly for y if we wanted to. And in fact, this one we could, because notice that this is a quadratic equation in y, but we'll just leave it like that because it's fairly typical just to leave these as implicitly described solutions. So just to reiterate, this is our implicit solution to our starting exact differential equation. Okay, let's do another. Okay, so here's our next example. We've got sine x times cosine y dx plus cosine x times sine y dy. So I've written it in that differential form just so that we're all used to it. But let's recall that that's equivalent to this guy right here, where we would like replace the dy with y prime and then leave off the dx. So let's start by checking that this is indeed exact. And we can do that by taking the derivative with respect to x of this function. So let's see, that's cosine x times sine y, and compare that to the derivative with respect to y of the coefficient function for dx. So that's going to be like sine x times cosine y. But the derivative with respect to x of cosine x is negative sine x. Sine y is like playing the role of a coefficient here. So this gives us minus sine x times sine y, but then that's exactly equal to what we get if we do the derivative with respect to y of the other one. So the fact that these are two are equal to each other means it is exact. Okay, so now that we know this is exact, let's state our goal, which will find our solution. And again, the goal is like described by the second half of the bottom of this board right here. Okay, so our goal is to find some function f of xy such that the partial with respect to x is this function, so our sine x cos y, and the partial with respect to y is this function right here, so cos x sine y. Okay, so let's get to it and see what we can have. So we'll start with this f sub x. The partial with respect to x is sine x cosine y. And we'll take the antiderivative of that with respect to x. So I'll just write that with this little integral symbol. So that's going to tell us that f of xy is equal to, well, the antiderivative of sine x is negative cosine x. So that gives us minus cos x cos y. And then from there, we'll take the partial derivative with respect to y, and then compare that to what we know is the partial derivative with respect to y. Oh, and I missed one thing. This should be plus g of y. So that's our kind of extra function of y as needed. Okay, so taking that partial with respect to y will give us something like this. We'll have cosine x times sine y. From taking the derivative of cosine y gives us negative sine y, and then plus g prime of y. So that's going to be equal to our partial of f with respect to y, but then bringing this down sets up some sort of differential equation that we can solve for g. So let's see, we'll have cosine of x times sine of y. We can cancel out those from both sides of the equation. This thing works very quickly. We get g prime of y equals 0, which means g of y is really just some sort of constant. But we don't really need to worry about it being a constant or it being added to this function because we have a constant built into this last step right here. Okay, so that means that in the end, we have a solution. And our solution is f of xy equals a constant where we don't need to worry about this g of y, given that we can absorb those constants into each other. So we have minus cos x cos y equals a constant. I would maybe even just like multiply by a minus sign and absorb that minus sign into our c, and we'll have cosine of x times cosine of y equals a new constant where I've absorbed that minus sign in. And this would be our implicit description of y as a function of x here. So let's look at our next example. We want to find conditions on the numbers a, b, c, and d such that ax plus by plus cx plus dy y prime is an exact differential equation. And then after we know those conditions, let's solve this differential equation. Okay, so let's get to it. For this to be an exact differential equation, we need the partial with respect to x of this term, so that's cx plus dy, to be equal to the partial with respect to y of this. So that's ax plus by. But those are really just linear functions in two variables. It's super easy to take those partials. So the partial with respect to x of cx plus dy is just equal to c, but then the partial with respect to y of ax plus by is just equal to b. So in order to have exactness, we need b to be equal to c. Okay, but that means our differential equation up here will change to the form ax plus by plus bx plus dy times y prime equals 0. So that's our new differential equation, which is guaranteed to be exact by this condition that we've instilled into it. Okay, so now we can solve it. So let's recall, in order to solve it, we need to find this function f, which by the way is called a potential function. That's really more in the setting when we're talking about the gradient of f being a vector field though. But sometimes we'll call this f a potential function. Okay, so anyway, our goal is to find capital F of xy such that f sub x is this function, so that's ax plus by, and then f sub y, the partial with respect to y, is this function. So let's see, that is bx plus dy. And now maybe just for a little bit of a different take here, let's start with f sub y and work towards f sub x. It's about the same though. So let's start with f sub y equals bx plus dy. So our first step is to take the antiderivative of this with respect to y. So that's going to give us our function f of xy equals, so let's see, this is going to be bxy plus d over 2 y squared, and then plus g of x. So since we took an antiderivative with respect to y here, we get our constant is actually a whole function of x. Okay, nice. So now what we'll do is take the derivative of this with respect to x and compare it to the known value for f sub x. So the derivative of this with respect to x will be by, and then the derivative of this guy, this d over 2y squared with respect to x, is 0 because we're doing partial derivatives here, and then plus g prime of x. So that needs to be equal to ax plus by, and that equality comes from the fact that we're just bringing this down here. Okay. Now cancel out what we can. We can cancel out the by from both sides of the equation, and we get g prime of x equals ax. But that means that g of x equals a over 2x squared. I don't need to put a plus constant in there because we get the plus constant, or we get the constant over here. Okay, so now we have all of the necessary information to write down our solution. Our solution is f of xy equals some constant. We have this portion of f of xy from this antiderivative, the g of x portion from what we did over there. So in the end, we have a over 2x squared plus bxy plus d over 2y squared equals some constant. That would be our solution. And let's make sure we see that as a lowercase c, so it doesn't look like the uppercase C that we started with over there. Then furthermore, I could just multiply both sides of this equation by 2, and that would give me something that looks a little nicer. So I've got ax squared plus 2 bxy plus dy squared equals our new constant, where we've absorbed the 2 into our old constant. So maybe we could strike this out, and then this would be a nice final form of our solution to this differential equation when we impose this exactness condition. Okay, now let's move on. So I've got 3 warm-up problems for you guys to practice what we went over today. So again, this is just solving exact differential equations. So the first is 2x minus 2y plus 12y squared minus 4xy times y prime equals 0. The second is an initial value problem. So we have y cubed minus 1 times e to the x dx plus 3y squared times e to the x plus 1 dy equals 0 with the initial condition y of 0 equals 0. And then finally, this interesting one involving exponential and trigonometric functions. We have y e to the xy tangent of x plus e to the xy secant squared of x plus x e to the xy tangent of x y prime equals 0. So even though you know that these are going to be exact differential equations because that's what we worked on today, I think just for practice, it's probably best to first check that they are exact differential equations and then go through the strategy that we outlined to find implicit descriptions for those implicit descriptions for the solutions to those differential equations. And that's a good place to stop.